All right, we're on to 10.4, day one, video number 3. Um, just continuing with our examples, find the area of the region enclosed by the rose curve r equals cosine of 2 theta. Okay, we've already graphed that one several times in the past. It's a 4-petaled rose. Each one of the petals are symmetric to the x and y axes in this case. So we need to find the integral of 1/2 of cosine of 2 theta squared d theta. Now the part here that we actually have to think about is how are we going to do this one? Because you can't just go from 0 to 2 pi on this one. And the reason for that is because you've got tangents at the pole, which kind of act like um, cusps in a way, and you can't really take an integral around or through the cusps. So if you remember how those worked, you had tangents at the pole at each of the pi fourths, 3 pi fourths, 5 pi fourths, 7 pi fourths, and so on. Um, we could find the area of one petal very easily by going from negative pi fourths to pi fourths. You can't go from 7 pi fourths to pi fourths because that actually goes backwards, so don't try and do it that way. You'd have to go from negative pi fourths to pi fourths, and you could find the area of one petal and then multiply it by 4. You could also use symmetry in the fact that the top half of that petal, if you start at 0, and just go to pi fourths, is going to be the same all the way around, so you'd have to multiply the whole thing by 8. It really doesn't make a difference which way you have to do it. You definitely would want to know, in this case, that you have symmetry to play with here. That's what's going to make this a little bit easier. So again, go back and look at the graph if you're not sure. We're going to use the symmetry and we're going to do the top half of the right petal. So we're going to go from 0 up to pi fourths. But because we want the area of the entire curve, we have to multiply that by 8 because you'd have 8 equal parts of those to do this. So that's what we're going to do. Nice thing is we can pull the 1/2 out to the front. 1/2 times 8 is 4. And then we've got cosine squared of 2 theta d theta. So we're going to have to use our reduction formula here because we got to get rid of that cosine squared to make this something easy to take an antiderivative. So we'll have 0 to pi fourths, and the reduction formula is 1/2 1 plus cosine of twice the angle. It's cosine of 2 times the angle, so it's not cosine of 2 theta anymore because the original angle given here is 2 theta, so we have to double it, so it's cosine of 4 theta d theta. Once again, now I have a constant multiplier of 1/2. I can pull that out to the front. We'll get 2. And I actually don't need the integral anymore. I apologize. I'm going to go ahead and take the antiderivative of 1, which is theta. Antiderivative of 4 theta. Again, kind of using our little trick there. We're going to have a 1/4 sine of 4 theta. And we're going to evaluate that from 0 to pi fourths. So plugging in pi fourths, we're going to get 2 times pi fourths. Plugging in pi fourths into the sine of 4 theta gives us the sine of pi. That's 0. That's gone. Plugging in 0 for both theta, both of the thetas, is also going to give us 0. So really what we get is 2 times pi fourths, which is just pi halves. So our area is pi halves. And that's for the entire rose curve. All right. So now we're going to introduce not a new concept, but a new concept to our polar. What if we've got multiple polar curves and we're trying to find something where the area is either in between, a part of, outside of, something like that? So let's go ahead and take a look at this example right here. We want to find the area of the region that's inside the cardioid 4 plus 4 cosine of theta. You can see that's the one that's kind of got the little heart shape. And then outside of the circle, r equals 6. That's just literally a circle with a radius of 6 centered at the origin. And you can hopefully see both of those on the graph. If we want to find the area of the region inside, so that's going to be basically, it says, I'm sorry, inside the cardioid, but outside of the circle. Inside the cardioid and outside of the circle is basically this region over here. Okay, the pen can't actually handle that thin little area, but it's that, basically that crescent moon looking area over there. Oops, change back to the pen. So in order to do this, what we have to think about is, this is going to be basically an outside minus inside kind of a concept. So if you think about when you had to take the area of a washer, you would take the area of the big circle and subtract the area of the little circle, and it would basically give you the area of the washer. It's the same concept here. If you think about it, you're taking the area using, oops, that's supposed to be in red, using the outside radius first, then you subtract off the area of that inside radius, and that's going to give you the area in between, the area of the washer. Same exact concept. We are going to take the outside radius and multiply it, and then subtract the inside radius area. Well, in order to do that, we need to figure out what bounds these two things. Well, you should be able to see that there are bounds right here and right there. So we need to figure out what angle creates this and what angle creates that piece right there. And then we can go in between those two. Those will be our alpha and our beta. And again, if you notice the symmetry here, we could use symmetry. It'll probably be easier, to be honest with you, to use symmetry. So that's probably what we're going to do. So we'll actually go from 0 up to the first one. And then we're just going to double the result because this is symmetric. So how do we find the intersection? Just like you would find the intersection of any other two functions, you set them equal to each other and solve. So we're going to have 4 plus 4 cosine of theta is equal to 6. Subtracting 4 on both sides, we get that 4 cosine of theta is equal to 2. So cosine of theta is then going to be equal to 1/2. Noticing that this is in the first quadrant, we don't need to worry about all the other theta values. Theta is going to be, let's see, cosine of pi over 3 would give us that 1/2. So we're going to end up going from 0 to pi over 3 for our integral. So we'll integrate from 0 to pi over 3, and that'll give us this piece up here. So we're going to double it to get the entire thing. That'll give us the bottom half as well, and it's 1/2. Now, it's the outside radius squared minus the inside radius squared. You don't subtract the two of them and square the whole thing. It's basically a pi r squared minus pi r squared like we did before. So it's the same idea. This is 1/2 r squared minus 1/2 r squared. So the outer one, which was the cardioid, and you can kind of see that visually, was 4 plus 4 cosine theta squared minus 1/2 of 6 squared d theta. Okay, well, the nice thing is that 1/2 can be factored out of both terms. Pull that constant out to the front. It gets rid of our 2. So that's actually really nice in this case. We are going to have to distribute the 4 plus 4 cosine theta, squaring it. So we're going to get, what's that, 16 plus 32 cosine theta plus 16 cosine squared theta. And then don't forget to square the 6. So we get minus 36 d theta. Okay, so let's go ahead and combine our constants. 0 to pi thirds. 16 minus 36 is negative 20, so we're going to have a 32 cosine theta plus 16 cosine squared theta minus 20 d theta. So 32 cosine theta and negative 20, easy to take the antiderivatives of. We're going to have to utilize our cosine squared reduction formula to get rid of that. I'm going to bring this over here just to give myself a little more room. So 32 cosine of theta plus, so that's going to be 16 times 1/2 of 1 plus cosine of 2 theta, and then minus 20 d theta. And let's simplify what we've got on the inside there. So we're going to have 32 cosine of theta. 16 times 1/2 is 8. Distributing that into the 1 is going to be 8. 16 times 1/2 is 8. Distributing that into the cosine of 2 theta will give us 8 cosine of 2 theta minus 20. And the only other thing that we can combine are our constants here. We've got an 8 and a negative 20, so that should give us a minus 12 at the end there. And then we'll be ready to take antiderivatives. Again, this process is not fast. 8 cosine of 2 theta minus 12. There's a lot of preliminary steps that go into this before we can actually do the calculus. So now we're ready to take antiderivatives. So 32 cosine theta, the antiderivative is negative 32 sine of theta. 8 cosine of 2 theta. The, excuse me, that's not a negative, that's a positive sine. Sorry, it's 32 sine of theta. Antiderivative of 8 cosine of 2 theta is going to be a sine of 2 theta. Remember, we have to introduce the extra 1/2 out in front now, which is going to make that a plus 4. And then we've got minus 12 theta. Evaluated from 0 to pi thirds. All right, let's see what we get. Plugging in pi thirds, we're going to get 32. Sine of pi thirds is root 3 over 2 plus 4 times the sine of 2 pi thirds, which is also root 3 over 2, minus 12 times pi thirds is 12 pi over 3, or 4 pi. The nice thing is plugging in 0 here gives me sine of 0, and 12 times 0. Those are all 0. Those are gone. So we're going to get 32 root 3 over 2, which is 16 root 3, plus 4 root 3 over 2, which is 2 root 3, minus 4 pi, or 18 root 3 minus 4 pi. Okay, and that right there gives us the area in between the two curves right there. So basically that crescent moon area. Again, not short problems, but doable. All right, find the area of the region common to the two regions bounded by the following curves. Okay, so this one, again, I don't expect you all to be able to do these, by the way, without using your calculator as far as graphing them, but I do expect you to be able to do the integration and everything by hand. So on your homework, you use the calculator if you need to be able to graph these, but you should be able to work them out by hand. We are going to set this one up because this is important to be able to see, but we are not going to finish solving it, although I will tell you the answer so that you can work it out on your own and make sure you can do it all. So if you plug this into your calculator, you're going to get something that looks like this. The negative 6 cosine of theta is a circle which actually sits on the left-hand side of the origin. So it's a circle over here. Okay, that should not have crossed over. Let's see how to do this the right way. Something like that. And then the cardioid, 2 minus 2 cosine of theta, is a cardioid where the heart piece, or the top of the heart piece, is on the right-hand side. So I'll do this in red. So it's going to look something like this. Comes out like that, intersects up here. goes kind of through the middle of the circle and does something a little bit like that. It is symmetric when you look at it. And again, you'll see in your calculator. So there's a trick to this one, which is why I only want to get this one set up for you guys, or help you set it up, because it says you want the area of the region in common. So you have a common space. I'm going to try my best to, oops, not crayon, highlight inside the lines. The common space is in here. We are looking for all of this area right here. But there's a problem. We can't just say, okay, well, let's just figure out one minus the other. It doesn't work that way in this case. The reason is, if you start here at the pole and we figure out where these intersections are, because that's important, look what happens. Oops, I completely missed the intersection. Look what happens when we hit the intersection. There's one intersection, and there's another intersection. What happens is you've actually split the shaded region, or the highlighted region, into two separate little regions in here. We have the region over here, and then we have the region in here. And that's if we're going to use symmetry, which we are going to do here. We're going to split this thing into the top half and go from here over, and we'll multiply everything by 2. But you've got two separate little regions in there. So really what you need to figure out is, how does this thing work? Well, you still need to find the intersection point, which we will do. This first region, we'll call this region 1, I guess, and we'll call this region 2. The first region is really only going to be in between, looks like pi halves, and wherever that intersection point is of the circle. That's all you have to do, is find the area of the circle in between pi halves and whatever the intersection point is. The second region, region 2, is going to be between your intersection point and it looks like probably pi, but it's only going to be within the cardioid. We don't need to worry about the region of the circle. That's going to add up to be the common region. So you have to separate this and do two separate integrals. So first of all, let's find the intersection. So we'll have -6 cosine of theta equals 2 minus 2 cosine of theta. So if we add 2 cosine of theta to both sides, we'll get -4 cosine of theta equals 2, dividing by -4 cosine of theta equals -1/2. And we know that that's in the second quadrant, which means that this is going to be at 2 pi over 3. So that's that angle right there. So you can see that we're going to go from pi halves to 2 pi over 3 for the circular region, and then 2 pi over 3 to pi for the cardioid region. We're going to add those two things up. We'll double the whole result, and then we'll get our area. So again, I'm going to help you set it up, but I'm not going to finish it. I will tell you what the answer is going to be, though. It's a good one to practice. So we know that we're going to double the entire thing to get our area. All right, so the area of the first region is going to be between pi halves and 2 pi thirds, 1/2, and that's the circular part, so that's going to be -6 cosine of theta squared d theta. And we're going to add that to the area of the second part, or region number 2, which is going to go from 2 pi thirds to pi, and that's going to be 1/2 of the cardioid part, which is 2 minus 2 cosine of theta squared d theta. Okay, so there's the setup of this thing. Believe it or not, this one actually works out to be a really nice answer at the end, and I'm going to tell you what that answer is. Again, I will leave it up to you to work through all the algebra and the antiderivatives and your trig stuff. This one actually works out to be 5 pi. So again, go ahead and work that one out on your own. All right, we are going to finish the last 2 examples, mainly because this one we're actually not going to do. This one's crazy. I don't know why I've left it on here. Probably just to show that it kind of looks interesting. But when you graph these things, because it wants to find the area of the region enclosed by these two graphs. First of all, r equals 2 over cosine theta is the same thing as r equals 2 secant theta. Although you probably won't plug in your calculator that way because most of the calculators can't do secant. You'll plug it in as r equals 2 over cosine theta. And then r equals 4 sine theta is a 3-petaled rose that looks something like this. Okay, they're all supposed to be equal amount. The petals should be equal, but I did not draw it very well. But that's what it looks like. And then the r equals 2 over cosine theta part is actually just a vertical line at x equals 2 if you were to plug that onto a rectangular coordinate plane. So what you're looking for is the area in this region right here. This one is actually pretty difficult to do. So we're actually going to skip it. It's not necessary to do. If you really want to try and challenge yourself, by all means, go ahead and do so. I don't even have the answer written down. It's been so long since I've done it, so I'm not going to write that down for you. But that's how you would set it up. It's a difficult problem to do, though. We will do the last example on here. So the area inside the circle with the polar equation, r equals 2 sine of theta, and above the lines with the equations y equals x and y equals negative x is given by. So we're trying to find the area, and the reason that this one's just a little bit more challenging is because of the fact that we're mixing polar and rectangular stuff here, but it's not that difficult to do. So r equals 2 sine of theta is a circle which sits up on top of the x-axis, something like that. And then y equals x and y equals negative x, those are your 45-degree lines, which cut through like this. And it says to find the area that lies above those two lines. So really what we are looking for is this area up in here. So as long as you understand that these are the 45-degree lines, and we should know what angle creates those, that is at pi fourths up here and 3 pi fourths over here. Or once again, you could use symmetry and go from pi fourths to pi halves and double it. This is a pretty easy one overall to do. So we are going to do the area is going to be equal to the integral from pi fourths to 3 pi fourths, or again, you could go pi fourths to pi halves and double it, of 1/2 of 2 sine of theta squared d theta. Okay, this one's pretty quick and easy overall. You will have to use a reduction formula. Let's go ahead and finish this off real fast. Squaring the 2 sine of theta is going to give us 4 sine squared. The 4 times the 1/2 will give me a 2 to pull out to the front. And sine squared, we're going to have to use a reduction formula on, so that's going to be 1/2 of 1 minus cosine of 2 theta d theta. I can pull the 1/2 out to the front, multiply it by the 2. My coefficients are basically gone. Actually, I don't need to rewrite that part anymore. I can take the antiderivative, so those are going to go away. Take the antiderivative of the inside, we get theta minus 1/2 sine of 2 theta evaluated from pi fourths to 3 pi fourths. All right, so plugging in 3 pi fourths, we get 3 pi fourths. Sine of 3 pi halves is going to be -1 times the -1/2 will give me +1/2 minus. Plugging in pi fourths, we get pi fourths. And then we're going to get sine of pi halves, which is 1, so it's -1/2. So putting those two things together, we get a 3 pi fourths minus pi fourths, which is 2 pi fourths, or pi halves. And then I've got 1/2 minus a -1/2, which gives me +1. So that area up there was pi halves +1. Okay, this was a very, very long video. I hate to tell you this, but day 2 will also include some relatively long pieces as well. but we'll come back with day 2 and start that one.